We're going to begin talking about the blood, and we'll do a quick overview as usual, and then we'll start looking at the different parts of the blood more closely, starting with the erythrocytes, and we'll move through to leukocytes and finish up with platelets and what they do for the body. So first up, let's just remind everybody what exactly it is that the blood does for us. So the principal purpose of our blood is to pick up oxygen from the lungs and then to circulate throughout the body and deliver that oxygen out to tissues, and then to also collect up formed carbon dioxide from the tissues, take that back to the lungs so it can be exhaled. And you might find this surprising, but we're going to learn when we get to looking at the lungs that actually the presence of that carbon dioxide in the blood helps to stabilize the pH. And the pH of the blood is really, really important. It stays within a very narrow range of about 7.35 to 7.45. And any time that we tweak that pH, either making it more acidic or more basic, we run the risk of actually inducing a fatal condition in the individual, because remember, the pH is can have a very large impact on proteins, and we're going to see shortly that the blood is made up of tons of different kinds of proteins. And if we tweak that pH, those proteins may denature, and that can spell death for the individual. Later on in 202, we're going to learn more about pH of the blood and how it's regulated and what can happen to an individual if the pH gets too far out of whack. Now, I know when you look at this, you might say, well, gee whiz, a pH is 7.35 to 7.45. That's slightly alkaline. That's not neutral. That's true. But because this is the normal range for the blood, we consider this kind of the neutral pH for the blood. Even though technically neutral pH is 7, in the case of the blood, since this is its normal range, we consider this neutral. So if I actually went to a value of 7.0 for the pH of the blood, that would be considered acidic in terms of blood pH, because it is below the value of 7.35, which is the normal range. So the blood also carries nutrients. We deliver things like glucose out to tissues, and vitamins, amino acids, lipids, all of these different things get transported in the blood, delivered out to the tissues, and we pick up metabolic waste products. The salinity of the blood, or the percentage of sodium chloride present in the blood, is at 0.9%. That's another critical value that has to stay within a very narrow or tight range. The blood also transmits hormones. We've already learned about hormones. We know that once hormones are secreted from a cell, they enter the extracellular fluid surrounding the cell, and then they eventually diffuse into the blood and are carried throughout the body. The blood also helps to regulate our temperature. When we're too hot, we have small blood vessels near the surface of our skin called arterioles, and when they dilate, they fill with more blood, and the blood carries warmth with it, and we can then release that warmth to the surface of the skin to cool off. When we're too cold, those arterioles close down, or vasoconstrict, if you will. And that helps reduce the amount of blood flow out to the skin, and thus we keep our core body temperature closer to our torso, and thus we don't lose as much body heat. The blood also contains lots of white blood cells in it that help to prevent infection, and it also has a bunch of different clotting factors and platelets that help to prevent the loss of blood, and also to help promote inflammation, which when we get to learning about the immune system, we'll find out is a key means by which we protect the body against foreign invaders. So there are some basic properties about blood I'm going to talk about very quickly. One is its viscosity. Viscosity means the thickness of a fluid. The viscosity of blood is much thicker than that of just regular old water, somewhere on the order of 4.5 to 5 times as thick as water. And that viscosity means that the heart has to work pretty hard to move that blood through all of our blood vessels. If the heart were moving water through our blood vessels, it would not have to work as hard. So this viscosity is really a result of the properties of cohesion. You'll remember water has the properties of both adhesion and cohesion. Adhesion means water molecules tend to stick to each other because of those hydrogen bonds you learned about. Cohesion means those water molecules tend to stick to other things like the proteins present in the blood, the interior of the blood vessel wall, etc. And that all contributes to the amount of resistance the heart encounters as it's trying to push that blood through the blood vessels. Another property of blood is its osmolarity. And osmolarity basically is a measure of how many dissolved particles are present in the liquid portion of the blood, which is called the plasma of the blood. Now, if the osmolarity becomes too high, then some interesting things can happen. In other words, if we have too many particles dissolved in the blood, then that draws even more water into the blood, and that increases blood volume, which leads to an increase in blood pressure. If, on the other hand, the osmolarity of the blood is too low, we have too few particles present in the blood. Let's say, for example, the kidneys aren't working properly and we're losing proteins from the blood in the urine. Then with too low osmolarity, there isn't enough attraction to pull water back into the blood from the tissues, so water tends to leak out of the blood. And as a result, we lose water from the blood volume decreases, and that leads to a drop in blood pressure. Obviously, the blood has cellular components to it, and it has liquid components to it, and we're going to talk about those starting with the fact that I need to remind you blood is a type of connective tissue. Remember from Bio 201, connective tissues have two principal components to them. They have cells, and they're not very cell rich. The number of cells is relatively small, comparatively speaking. And then there's this other component called the matrix of the connective tissue. Most of the connective tissues you learned about, the matrix was something like collagen fibers, elastin fibers, ground substance, that kind of clearish soluble substance. In the case of blood, we don't have solid collagen and elastin fibers. What we have instead is blood plasma. That's the matrix part of blood. Blood is a type of connective tissue because it meets a definition by having cells and a matrix component, and because it's derived from another type of connective tissue, bone marrow. Now, if we were to divide out and look at the matrix and the cells independently as the parts that make up the blood, let's start by looking at the matrix component, which consists of plasma. Plasma accounts for roughly 55% of the total volume of blood, and it's made principally of water. You can see over here the plasma component of blood consists of 91% water. It has about 7% proteins and then a few other solutes such as sodium chloride, some waste products, certain gases like nitrogen gas that are present in there. So far and away, water is the largest component of the plasma. We're going to talk about proteins in a minute, and I'll give you some examples. Well, I can give them to you now, come to think of it. Some different examples of proteins that are found in blood. You find lots of different what are called albumins, which is a class of proteins very common in the blood. They're the smallest type. They're the most abundant type of protein found in the blood. They help to transport hormones. They do a number of other things as well. There's also globulins. Globulins are, there are several classes of globulins, but they comprise the largest type of protein found in the blood plasma, and they include the gamma globulins, which another name for them are immunoglobulins or antibodies. So they're part of the immune system. There are also what are called alpha globulins. There are beta globulins as well. There's also, among the proteins, fibrinogen. Fibrinogen is a clotting protein. It's a precursor to a clotting protein called fibrin, which we'll learn about later. Now, with the exception of the gamma globulins, all the others that I've mentioned here, except gamma globulins, are made by the liver. So if you have liver malfunction or liver failure, this can have a profound impact on the the proteins that are present in the plasma, and it can actually drop the osmolarity of the plasma. And when the osmolarity of the plasma drops, we lose fluid from the blood. Now, this fibrinogen component of the plasma, I said, is the precursor for blood clotting. If we allow blood to clot, let's say you withdraw some blood from a patient, you put it into a vial, and you let that vial sit for a period of time, stasis or non-movement of the blood will induce clotting of the blood. And if we clot the blood, what we're really doing here is we're removing the fibrinogen. And when we remove the fibrinogen, what we have left over is this thing called blood serum. So blood serum is basically the liquid portion left or out after we clot the blood. So clotting the blood means we remove the fibrinogen, but it also means things like the red blood cells, the white blood cells, etc., the platelets get clotted out. And we're left with just the liquid portion of the plasma minus the clotting proteins in all the cells. Okay, I think, did I skip over one here? Nope, I didn't. Okay. Now, before I talk about the types of blood cells that are present in the blood, that's the cell part of the matrix, let me just talk about a couple of problems that can arise if I have issues with the proteins component of the blood plasma. So let's say, for example, we have a protein deficiency. For example, in Africa, it's very common in areas of starvation for young kids to have this condition like this child does here, where they have this very swollen, distended abdomen region, and then they have very spindly arms and legs. And this is a outcome of having a very protein-poor diet. And when we have a very protein-poor diet, we develop a condition called hypoproteinemia. That means very low protein in the blood. So as I said, causes can include things like starvation. Sometimes kidney diseases will cause the loss of lots of protein from the blood. And people who suffer severe second and third degree burns over large portions of the body can also lose a lot of protein very rapidly. When a person develops hypoproteinemia, the osmolarity of the blood drops, as I said before. That means we have fewer dissolved solutes present in the blood. And when that occurs, the fluid that is present in the blood tends to be pulled out of the blood. Because, and let me draw this here for you. Imagine you have the blood here inside of a blood vessel. Here are the tissues out here. Normally, the concentration of proteins inside the blood is very high relative to the concentration of proteins in the extracellular fluid. So normally, what this means is that water will be drawn in to the blood to try to dilute out this high concentration of solutes present in the blood. But if we have a condition where the amount of protein in the blood drops and becomes lower than out here in the extracellular fluid, then now water tends to be drawn out of the blood, and it begins to accumulate in the tissues as it tries to dilute down the higher concentration of solutes present in the extracellular fluid. This causes edema. Edema means the accumulation of fluid in tissues, and it's particularly prominent in starvation patients like this youngster here by accumulating in the abdomen. You can see that we have this very swollen looking abdomen. That's not because the kid's stomach is full of food. It's full of fluid that has been drawn out of the blood and into the abdomen. This is a condition called ascites when we get this accumulation of fluid due to hypoproteinemia. Very common condition we see in children with a condition called kwashiorkor. Kwashiorkor literally means displaced child. What this refers to is in African countries, when a baby is being fed breast milk, that baby gets sufficient protein to remain relatively healthy. But as soon as that mother gives birth to another child, well, that new baby gets to be breastfed, and the older child gets taken off breast milk and put on a very protein deficient diet. And that's when they develop this ascites, or what we call kwashiorkor, which means displaced child. Okay, If we don't correct kwashiorkor, the ultimate result is that that child will become severely dehydrated and will eventually die. All right, so we've talked about the matrix component of the blood. Let's talk about the cell component of the blood. These are what we also refer to as the formed elements. And there are three types of formed elements in the blood. The most common by far and away are the erythrocytes, or red blood cells, and they account for somewhere around 4.2 to 6.2 million red blood cells per cubic millimeter of blood. So they are by far and away the most common component. Platelets, which are little pieces of cells, they're not whole entire cells in themselves, but little tiny pieces of cells, only account for about roughly 250,000 to 400,000 cells per cubic millimeter. The white blood cells account for somewhere around 5,000 to 9,000 cells per cubic millimeter. So you can see by this that obviously the majority of the formed elements of blood is red blood cells. Then the next most common component are the platelets, and the least common are the white blood cells. And I want to erase this here so I can write a little bit more information out. If we look at red blood cells in the blood, there are a couple terms you'll hear used relating to the red blood cell component. One of these terms is hematocrit. Hematocrit really means the percent of the blood volume that is red blood cells. Now, I want to be real clear here. We're saying the percentage of the blood volume that's red blood cells. When a person gets dehydrated, the amount of fluid present in the blood drops, but the number of red blood cells stays the same. Even though the red blood cell count stays the same, the hematocrit's going to change because hematocrit is a measure of number of red blood cells per volume. And if the volume drops, well, then the hematocrit's going to increase. Red blood cell count is what I gave you already, that 4.6 to 6.2 value. And that's for men, by the way. Women have a slightly lower red blood cell count. But that's just the number of red blood cells per millimeter cubed, as I said before. Okay, platelets, I'm going to reserve talking about those until near the very last of the lectures in this series on the blood, and we'll get into more detail about platelets. For now, you just need to know that they are contributing elements to the formation of blood clots. As for leukocytes, or white blood cells, we can divide leukocytes into two major classes. There are 5 types of leukocytes, and we can divide those out into 2 groups. Something called granulocytes, and the other group is called the agranulocytes. Remember, cyte means cell. Granulo means having a grainy appearance to the cytoplasm. So the granulocytes are the 3 types of leukocytes that have a grainy appearance to their cytoplasm. They include the neutrophils, the eosinophils, the basophils. You'll learn more about these in lab. The agranulocytes mean not grainy cells. These are cells where the cytoplasm appears pretty clear, relatively speaking. These include the monocytes and the lymphocytes. Oh, one more thing here. The amount of each of these varies in the blood, and the most common by far and away are the neutrophils, followed by the lymphocytes, then monocytes, then eosinophils, and then the rarest or the least common are the basophils. Easy way to remember this: never let monkeys eat bananas. Okay, next set we're going to talk about how we make blood, or the process of hematopoiesis.